So the next very important and interesting dynamic programming, the other very interesting example of dynamic programming is called longest common subsequence, or also called as LCS, right? So first let me explain what the problem is and then give you some examples. Imagine I have two strings. Let's call them S1 and S2. Okay, I'll take a couple of examples. So let's take example 1. Okay, so the problem is as follows. Imagine I have two strings. Let's say the first string is A, B, C, D, G, and H. Okay, basically this is basically a string of characters, right? And let's assume the second string that I have is A, E, D, F, H, R. Let's say these are two strings that I have. Okay, so the longest common subsequence of S1 and S2 is determined as follows. The core idea is this. So here A and A. So if you see these two, they're matching. Now if you see D, okay, the B and E won't match, right? E and C won't match, B and D won't match, C and D won't match, but D and D will match, right? Similarly, if you notice H also will match. So longest common subsequence is basically a subsequence. Okay, so ADH is called the subsequence of S1. Okay, ADH is called the subsequence of S1. Okay, so ADH is a subsequence of S1. Remember, for something to be a subsequence, it need not be a substring. Substring is different from a subsequence. Substring basically means ABC is a substring of ABCDGH. Substring basically means all of these characters need to be continuous or contiguous. Okay, for it to be a substring. Here we are calling it a subsequence, right? ADH is a subsequence of S1. Similarly, ADH is a subsequence of S2 also, right? Now, the longest common subsequence of S1 and S2 is basically a subsequence of S1 and S2 such that its length is maximal. So, for example, there is no other. So, for example, AD is a common subsequence. AD is a common subsequence between S1 and S2. Similarly, if you notice AH, right? AH is also a common subsequence between S1 and S2. But the longest common subsequence is ADH. And this is of length, and this is of length 3. So the longest common subsequence is a subsequence of string S1 and S2, right? And I hope you understood the concept of a subsequence. It's not a substring. Very important to note. If you pick any sequence of characters, as long as they're in this sequence, that is called a subsequence. So like ADH is a subsequence, ABC is a subsequence, ABD is a subsequence. As long as you maintain this order, it is called a subsequence. Now there are many common subsequences, like AD is a subsequence of S1. Similarly, AD is a subsequence of S2 also. Similarly, AH is a subsequence of S1 and AH is a subsequence of S2. But the longest common subsequence of S1 and S2 is ADH, which is of length 3. So longest common subsequence is pick up that subsequence amongst all the subsequences between S1 and S2 or common subsequences between S1 and S2 such that its length is maximal. Its length is maximal, right? Maximal length. You will not find any other subsequence of S1 and S2 which is common between S1 and S2 and which is longer than ADH. Okay, that's one example. Let's look at another example. Okay, just to make this more concrete. Okay, imagine if I have two inputs like this. Let's say AGG, my S1, let's assume, is AGG TAB. Okay, let's assume my sequence S2 is GXTXAYB. Now, if you notice, what is the longest common subsequence here? So, if you notice that G is common, T is common, A is common, and B is common. So the longest common subsequence between S1 and S2 is GTAB of length 4. Right? Because look at this, GTAB is a subsequence of S1, GTAB is also a subsequence of S2. And you can't find a longer subsequence of length more than 4. There may be another subsequence of length 4, but nothing which is larger than length 4. Okay, so this is the core idea of longest subsequence. Now you might wonder, why do you care about this? What are the applications of this? What are the applications of longest common subsequence? This is actually very, very useful in genomics. Okay, this is very, very useful in genomics. Imagine if you take the genetic code of a person or of an animal as a string S1, it will consist of 4 characters A, G, T, and C. Okay, and it will contain a very, very long string with billions of characters. Right? And it will only consist of these 4 characters. G, A, T, T, A, G, so on and so forth. Now imagine if you have 2 genetic strings like this. Let's say A, T, C, G, T, C, A, so on and so forth. Now finding the common or the longest common subsequence, finding the LCS of these 2 genomic sequences will give us a sense, a biological sense of similarity, between these 2 sequences. Okay, the length of the longest common subsequence and the longest common subsequence itself gives us a biological measure of similarity, which is used by genetic scientists and biologists to determine how similar these 2 gene codes are, right? So it has certainly applications in genomics. A more computer science driven application is as follows. Imagine if you have a file, okay? Imagine if you have a file 1 and file 2, right? Suppose I have file 1 which was modified by somebody to create file 2. If I want to exactly find where all file 1 is modified and where all file 1 is not modified to create file 2. Let's assume I have 2 files. These could be text files, these could be code snippets, right? Whatever it is. Imagine I have 2 text files basically. Okay. If file 1 has been slightly modified to create file 2, there is this program in Unix called as diff, right? It's there on most Linux boxes, Mac also, and I think in the Linux subsystem on Windows also. Diff tells you what all parts of file 1 and file 2 are exactly the same and what all parts have been modified. Okay, diff is basically a Unix command. It's there on most Linux distributions and on Mac. I know that for sure. I think it's also there on the Windows, on the Linux subsystem on Windows 10. Okay, so this function is extremely powerful and it's been used extensively to compare how much code change has happened. Imagine there are multiple programmers who are changing the code, right? So you can easily measure how much code has been changed from file 1 to file 2, right? So to do that, you want to find the longest commons. If you think of each of these files as a string of characters, right? You can find how much overlap is there using longest common subsequence. Actually, we use longest common subsequence at applied courses for some of our courses, like our AI course, where we check for plagiarism, of code, because we give some code assignments. If 2 students have if one student has copied from another student, their code will be very, very similar, right? Except for small changes here and there. So we do use longest common subsequence at applied courses itself for some of our courses like AI course to determine if students have copied code from one another. Again, LCS is a very small component of a very big system that we deploy. One of the algorithms that we use is LCS to compute how similar these 2 codes that 2 students have submitted for assignments are. Okay. But again, diff is a much more general purpose software. Okay. So I hope you got a good sense of why longest common subsequence is useful. Now, since we got a sense of why LCS is useful, let's go and actually solve the LCS problem. Okay. So let's actually define the problem very clearly. let's assume I'm given a sequence X, right, which is of length 1, 2. Suppose this is an array, let's say. Suppose X, let's assume, stores my string S1, and let's assume Y stores my string S2, right? So 1, 2, these are the indices, right? So this is of length M, right? My string S1 is of length M. My string S2 is of length N. Okay, I have two different strings. Of course, their lengths could be very different. Okay, so let's call them as string X and string Y. Okay, now the fun part is this. So let's actually write the recursive formula. Let's actually write the recursive formula. Right, actually write the recursive formula to compute LCS. Okay, you can actually compute longest common subsequence between X and Y using recursion. That's the power of it. And this is the innovative part of it. This is the innovation, right? This is the creative part of problem solving. Okay, you can actually show that the longest common subsequence. Okay, so instead of writing X with all of this, I'll just write it as the longest common subsequence of M minus 1 and N minus 1. So when I say M minus 1 and N minus 1, what do I mean? When I write this, I mean X from index 0 to index M minus 1. So when I write N minus 1, I mean Y from 0 to N minus 1. That's what I mean inherently. Okay. So let's write this problem definition in a recursive fashion. Okay. LCS of, so instead of writing this X whole thing here, because that will become very cumbersome, I'm just writing longest common subsequence of string X from index 0 to index M minus 1 and Y from index 0 to index N minus 1. Okay, let's try to define this recursively. Okay, so this is a very, very critical part of the problem. Okay, if I can write this as a recursive problem, okay, let's first write it. Let's first write this as a recursive part. Okay, so I'll write this as follows. So there are two cases here. Let me explain the cases here so that we can fill in the gap here. Okay, so imagine my X. Suppose let's take the example, right? Let's take these two examples. Let's say AGG. It's easier to understand with an example. TAB is my X. Okay, and let's assume this is my Y. What is my Y now? G X T X A Y B. Let's assume this is my Y. Okay, let me just cross check it. AGGTAB GXTXAYB. Yes. Okay. Now the longest common subsequence between both of them would be, again, this is the big idea here. If the last digits or if the last characters are the same, look at this. This is B, which means they are guaranteed to match. Right? If the last two characters in X and Y are the same, right? Or in other words, if X M minus 1 is same as Y N minus 1. If they both are the same, then the longest common subsequence of X and Y can be written as the longest common subsequence of X from 0 to N to M minus 2 and of Y from 0 to N minus 2. So let me write it. So this is LCS of M minus 1 N minus 1 is equal to LCS of M minus 2 and N minus 2 plus 1. Why is it 1? Because these two are anyway matching. Because the last characters are matching. Okay. So it is equal to LCS of M minus 2 comma N minus 2 plus 1 if the last characters match. Okay. Remember, I'm trying to define this recursively. If the last characters don't match, otherwise. Okay. See, look at this. If the last characters match, the idea is this. It's a very innovative idea. The idea is if the last characters match, then let's match them. When I have this match, my length of the LCS will increase by 1. Right? This is increased by 1 here, if you notice. Then, if I compute the longest subsequence since I match both of them, let's cross them off. What are the strings that are still left? X from 0 to M minus 2, Y from 0 to N minus 2. So I'm defining LCS on a larger problem, right, of M minus 1 comma N minus 1 as LCS on a smaller problem. If they both match. If they don't match, okay, that's also an important case, right? If they don't match, what do we do? So let's take this, right? Let's take another example. Okay, let's take example B. If they don't match, okay, let's assume I have these two strings. My X is A, B, C, D, G, H, right? Let's say my Y is A, E, D, F, H, R. Where the last two strings are not matching. So the LCS, otherwise case, if the last two, not string, the last two characters don't match here, then the LCS of X and Y can be written as the LCS of, right, X, the whole X. Okay, I'll write it as LCS of the whole X itself, right? LCS of M minus 1, and I will say, see, because they both are not matching, right? I can try to match X. I can try to match X, the whole length of X, to the length of Y except the last character. Because anyway, the last characters are not matching. Look at this. H and R are not matching. So what I'll try to do now is, I'll try to match X, the whole length of X, from 0 to M minus 1, with Y from 0 to N minus 2. I'll try to find this. And similarly, I'll try to find LCS of, okay, the other way around. I'll try to match all the N minus 1 characters. Okay, let me change the color here. The first thing that I'll do is, I'll take all the N minus 1 characters of X. Look at this, all the N minus 1 characters of X, and from 0 to N minus 2 characters of Y, and try to match, and try to find the longest common subsequence between this white underlined part and this white underlined part. That's first part. The second part that I'll do here is this. Okay, the second part I'll try to do is, I'll try to find the longest common subsequence between this part from 0 to N minus 2 and the whole of Y. Okay, this is the second part. From 0 to N minus 2 and from 0 to N minus 1. Between these two, right, I could get one longest common subsequence here and one longest common subsequence here. I will take the max amongst both of them. Because these two possibilities are possible, right? Look at this. Either the last character matches. This is case 1. This is, let's call it case A. What is case B? In case B, the last two characters don't match. Then I'll try to match this whole string with the whole string of Y except the last character. And that's what is this part. And I'll also try to match all the characters of X except the last one, except this last one, which is this, and all the characters in Y. And between these two, whichever is larger, I will pick that up. Okay, so this can be written as max of LCS of M minus 1 comma N minus 2 and LCS of M minus 2 comma N minus 1. Okay, if you notice, there's a very important observation here. Initially, you have a problem of size M minus 1 comma N minus 1, which you are now breaking down into a problem of size M minus 2 into N minus 2, sorry, M minus 2 and N minus 2, or you are breaking that problem into M minus 1 and N minus 2, or M minus 1 and M minus 2 and N minus 1. Okay, it's a tongue twister because of M and N, but I hope you understood this, right? See, M minus 1, N minus 1, I'm breaking it into M minus 2, N minus 2, or M minus 1 and N minus 1. So this is a sub-problem. Remember, this is a smaller problem than this. Similarly, this is a smaller problem than this because I have one less here. Here and here, I have one character less, right? Or this is solved using this, where even here and here, I have one character less each. Okay, and this is the recursive formulation, right? This is the whole recursive formulation of LCS. Now, if you notice, let's actually draw the recursion tree. Okay, so if I have a problem of size M minus 1 and N minus 1, it can be solved in one of the three ways. Either if the last two characters match, I'll solve with this. If the last two characters don't match, then I need to solve M minus 2, N minus 1 and M minus 1 and N minus 2 and pick the max between both of them. Okay, so either see the last, so this is the match. This is basically for match. If they don't match, I have to find the max between both of these. Okay, to solve a problem, this is a recurrence relation where you have two variables, not one variable. Okay, now I can break this further. This will be broken further into m minus 3, n minus 3, or it will be broken up into m minus 2 and n minus 3. Reduce this by 1, then reduce this by 1. Okay, now again, this will be broken up into 3 problems. Okay, it will either be m minus 3 and n minus 2. See, reduce this by 1, reduce this by 1. That's the first option. If they both match, this is match case or the max case. There are only 2 cases. This is the match case and this is the max case. Right? Here what happens? It becomes m minus 3 and n minus 1, or m minus 2 and n minus 2. Right? So similarly, you can also write this into 3 parts. Okay, the match case. In the match case, what happens? M minus 2 and n minus 3. Right? In the max case, what happens? You will have, again, because the recurrence tree will become very, very complex. Here, what happens now? M minus 2 and n minus 2. Reduce this by 1. Here, I'll reduce m minus 1 and n minus 3. Okay. So now if you notice, there is a lot of overlapping subproblem. Look at this. Here I have this. The same thing is also here. The same thing is also here. Okay, look at this. From the recurrence relation, see the 2 properties that we have to satisfy, right? Let me go back to that step. Right? There are 2 properties, optimal substructure and overlapping subproblems. Right? I'm sorry. So we already saw, So we already saw the optimal substructure here. Okay, if you notice, this basically shows optimal substructure. This already shows optimal substructure. And why does it show that? Because given a problem of size, given a larger problem here, I'm able to obtain the optimal solution to a larger problem using solutions of smaller problems, either this or this or this. Okay, the word optimal, I hope, makes more sense now, right? Because to find the optimal or the longest common subsequence of a larger problem, I can find it by solving for substructure. The substructure here basically means that I can solve this using problems which are smaller, right, than this. Okay, by solving problems which are smaller than this, but which are exactly the same, right? Or in other words, if I can represent this like a recurrence, like a recursion type of structure, I have the optimal substructure here, right? The second thing that we need is overlapping subproblems. The second thing that we need is overlapping. The second property that we need is overlapping subproblems, right? So here I've shown you that n minus 2, n minus 2 is being repeated in multiple parts of the recurrence tree. Similarly, there will be more things. If you actually draw it longer, if you actually draw this longer, look at this. There is this m minus 2, n minus 2, right? Is it there? M minus 2, okay, m minus 3 and n minus 2, right? Okay, here you have this again. Same problem being solved twice, right? Look at this. Again, you have m minus, let me change the color again. You have m minus 2, n minus 3, m minus 2, n minus 3. Okay, you have the overlapping subproblem because in the recursion tree, the same problem is being solved in different parts of the recurrence tree. Suppose if I solve it once, if I solve the problem once here, why should I again solve it here? Or if I solve it here, why should I solve it here? Look at this. Why don't I store this data and reuse it, right? So because longest common subsequence satisfies both these properties of optimal substructure and overlapping subproblems, as we have seen now, we can certainly apply dynamic programming. We can certainly apply dynamic programming to this. Okay. Suppose if I don't apply dynamic programming, I simply write the recursion approach of it without any dynamic programming. What would be the time complexity? Let's just quickly analyze that, right? So this problem, okay, let's assume I don't get the match. Let's assume every time I get the max. So this problem is broken up into 2 problems of the same type. Now this problem is again broken up into 2 problems. Now this problem is broken up into two problems. Let's assume every time I go through the max approach. Because if you go to the match, a problem is broken down into problem of its own type. Here I have two problems, right? So 2 times. Okay, here I have 2 subproblems. Here I'll have 4 subproblems. Okay, next level down I'll have 8 subproblems and so on and so forth. You can show that the time complexity for this is order of 2 power k, right? Where k would be max of m comma n. Look at this, very simple to understand, right? The longest depth that you'll see, if every time a problem, look at this, we've seen this multiple times. This is a problem which is broken down into 2 problems. Now this again, let's assume gets broken down into 2 problems. This again gets broken down into 2 problems. Okay, so how many problems I have here? 2 problems. How many problems I have here? 4 problems, right? Yes, the next time I'll have 8 problems, so on and so forth. 2 power some h problems, right? Now if you notice, your n minus 1 only decreases by 1 here. Your m minus 1 also decreases by 1. So what is the maximum height of this whole tree? It will be the max of m comma n, right? That will be the maximum depth. And look at this. I have 2 power 1, 2 power 2, 2 power 3. We have seen these types of recurrence trees many times. If you keep doing it, the total time complexity will be order of 2 power k, where k is equal to max of m comma n. Which means if you write the simple recursion approach to it, this will be an exponential time complexity algorithm. Can we do better than that? Obviously, because that's the power of dynamic programming, right? I have a problem which is exponential time complexity, but the beauty of it is it has optimal substructure and overlapping subproblems, which means I can store this data. I can store this data in a 2-dimensional array. Imagine if I have a 2-dimensional array like this. Imagine I have a 2-dimensional array like this. Okay, a 2-dimensional array can be thought of as a matrix, right? Let's assume all of my m's are here, all of my n's are here. Okay, I'll just simply store, let's assume L00, I'll store L11, L12, L13. I'll keep storing this in this matrix and I'll reuse them. Okay, that is the core idea. That's the core idea of whole of dynamic programming now. Okay, let's actually write some simple code to do it. Okay, let's actually write some very simple code to do it. Okay, let's actually write it down. Okay, very simple. Okay, so I'll write some pseudocode for it. Let's assume I have this function called LCS. Okay, and I have strings x and y, which are of lengths, let's say m and n. Let's just say. Okay, so I'll create now an array called L of length m plus 1 and n plus 1. Okay, I'll just create this. So this is basically a 2D array that I'm creating. This is basically a 2D array. Okay, now what I'll do here is this. For I equals to 0 to m, here I'm assuming that the strings are represented from 0, 1, 2 up to m, not m minus 1. Similarly, y 0, 1, 2, so on, n. Okay, so the strings are actually of length m plus 1 and n plus 1. Okay, not m and n. Okay, so what am I doing here? For I equals to 0 to m, similarly for j equals to 0 to n, right? So now what I'll do here is this. Okay, so this is basically a twin loop. Okay, what I'll do here is this. If I equals to 0 or j equals to 0, right, then Lij is equal to 0. Okay, obviously, right? If the lengths are 0, of course, the longest common subsequence will be of 0 length. Else, let me just scroll down. Else, right, if x of I minus 1 is equal to y of j minus 1, right, then Li comma j is equal to Li minus 1 comma j minus 1 plus 1. This is the last character match. This is the last character match case, right? That's what it is, right? Else Lij equals to, let's assume I have the max function, max of, right, Li minus 1 comma j, right, and Li comma j sorry, j minus 1, right? We'll decrease both of them, right? That's what it is. So this is basically a twin for loop. If you think about this is one for loop, this is the other for loop. Okay. Finally, I'll return L, M, comma, N. That's it. That's all. That's all is the function here. This is my LCS function. Now, if you notice, what did I use here? I used a bottom-up approach here. So we used a bottom-up approach or tabulation, right? We tabulated the whole data. Why is it called a bottom-up approach? Because initially I'm computing LCS of 0, 0, then 0, 1, then 1, 0, then 1, 1, so on and so forth. So we're going from 0, 0 up to m, n. Right? That's why it's called as bottom-up approach or tabulation method. Right? If you look at the time complexity of this, it's trivial, right? I have two for loops. One for loop which runs m times, other for loop that runs n times. So the total time complexity here is order of m into n. And the space complexity, because I have this L, I have this array L, the two-dimensional array, it will be order of m into n. Right? So what have I done here? We have taken an exponential time algorithm using simple recursion and converted it to a polynomial time algorithm. Right? Why is it a polynomial? Because I have two parameters here, m and n, and they're being multiplied. Okay. So LCS, this is again, we can also do a top-down memoization like solution also, but it's easier sometimes to write the bottom-up approach. Okay. Very simple code, very straightforward code. Okay. So I hope you understood this, right? So this is basically the recursion case. This is the otherwise case, right? This is the last character match case. That's all. That's all there is. And we're just doing this twin loop. And this is the boundary case, right? If I equals to 0 or j equals to 0, we are saying Lij equals to 0, right? Very simple code. Time complexity is also very simple to compute. And all of this is possible because dynamic programming works well when I have overlapping subproblems and optimal substructure. That's the key idea here. Okay. I hope you got an appreciation of longest common subsequence, especially the power of dynamic programming to solve the longest common subsequence problem.